We are live. So tonight really isn't a content-related stream. It's kind of more of an open discussion type of deal. I'm really here just to answer any and all questions you have about AP Chem, about the content, what it's like in the course, stuff like that, and really how to actually, do well on the exam, so that you guys know what to expect from a student perspective, from a teacher perspective, etc. So let's just get started here. All right, what is the format of the exam? Okay, geez, let's see if I remember this. Okay, so you will have 60 multiple choice questions, and I believe you get 75 minutes to answer them. So they'll be just normal, multiple choice questions. You'll get just like A, B, C, D. And then the questions will usually focus on some sort of scenario. So it's a lot less of just rote calculation than it is being able to apply the concepts that you learn. So for example, here, let me pull up a practice test, and I'll be able to show you what I mean. See if there's just an open one. If not, then that's okay. No, I can't find a real one. But yeah, it's really a lot less of just rote knowing how to do calculations, and a lot more of application of the concepts that you learn. So you might get a question that says, for example, which of the following elements displays the highest metallic character? And then you'll be able to say, oh, well, neon doesn't lose electrons, it's a noble gas, and then from there you can say, okay, that's wrong, and then you can eventually get the right answer. So it's a lot less of just calculating. The free response, that's where you're going to be doing a lot more of the math, because you're not allowed a calculator on the, here, let me just add that as a question. Yep, if you guys have any questions, hi Jeffrey, if you guys have any questions, just drop it in the ask a question area so that I'm able to directly address those. The chat is really for you guys to discuss. The chat, I'll be able to see it, but any questions that you have, just drop in the box. So the free response section, you will mostly be doing, and here I can actually pull up free response questions for this, and these are the ones that I actually took. So I just have to find them real fast, and then I'll be able to show you guys what I mean by the difference between the multiple choice and the free response. One sec. There it is. Let me share my screen here for a minute. There it is. All right, so let's take a look at these. Obviously, you might not know how to do them, and that's okay. It's still September. But so with the free response, you get a periodic table just like this, and you're not allowed to rip it out. So, that's what it says, do not detach. But yeah, you get a normal periodic table. It doesn't tell you the names, so you should learn your chemical symbols, but that comes with use. It gives you molar masses, stuff like that. Then you're given all the formulas. So it's nice that you're given, geez, my dogs are going crazy. It's nice that you're given them. And then you can see the questions usually give you some sort of scenario. So you can see here we have urea, used in chemical fertilizers, and then they ask you a bunch of questions about urea and what it has to do with this and that. And so with the free response questions, there are 3 long ones. So there's usually like 8 or 9 parts to it, give or take. So you can see there's another one with like 8 parts, and then another one with up to H. And then there's 4, 5, 6, and 7 are short questions. So you can see just like describe the effect of raising the temperature. And these are the questions really, they're going to ask you to do calculations, but they're going to be more real calculations because you have a calculator for this section. So for example, let me see if I can find it. Here, he determines that 5.9 grams of this, and they give you the molar mass, can dissolve in water to make 5 milliliters of a saturated solution. So that's where you'd use those numbers to do a legitimate calculation, as opposed to the multiple choice, where not only will it be nicer numbers, but you won't be doing as many calculations. So yeah, let me close that question there. I don't know, I forget how long you get for the free response. It's 7 questions. You get 1 hour and 45 minutes. So you get more than enough time to do them if you know what you're doing. It can be very daunting though. All right. And be sure to, when you go through the questions, you can read through them and see, you can upvote the ones that you want to see answered first. I'm just going to go down the list. So yeah. So just go through and upvote whatever you want to see answered first, and I'll be able to know what you guys want to, first. All right, how do I use dimensional analysis? All right, that's a really good question, because dimensional analysis is, in my opinion, one of the most, if not the most, important concepts in AP Chem. Because if you don't know how to do dimensional analysis, you're kind of screwed for the rest of the course. Because really, all of the problems boiled down to just converting between units, right? You're going to be converting from milliliters to liters, from this to that. And so if you don't know how to do that, it can be a problem and can really help you. So really the way I like to do it, and I'm pulling up just an online whiteboard here, is that, so let's say you have some unit, right? You have some starting unit. I'm going to call that just, I'll just write down start. And you want to convert that to some ending unit, right? The way we do that is through a conversion factor, right? And that's different for every unit, but it's a conversion factor. And my handwriting is trash on here, but I'm doing my best. So how we do that is we basically have our starting unit, right? So that could be meters, milliliters, moles, whatever. And we multiply it by the conversion factor. And at the end, we want our ending unit. So what we want is we want our ending unit on the top and our starting unit on the bottom. So this could be, for example, 1,000 kilometers over, or 1,000 meters over 1 kilometer. And that's how you convert from meters to, from kilometers to meters, for example. So here, yeah, let's do that as an example. So let's say we have 3 kilometers, right? And we want to convert that to meters. We would want kilometers on the bottom. And then we know that there are 1,000 meters per kilometer. And so the kilometers cancel out, and we get 3,000 meters now, right? So that's how really dimensional analysis works in AP Chem, and why it's so important. Because you might have to do this, but with more complicated units, or you might have to daisy chain them together. And it's really something that if you are having trouble with it, something that you want to be able to practice really efficiently. So yeah. Here, let me make myself big again. Here we go. What's the difference between enthalpy and entropy? Okay, geez, you're taking me back to my thermo days. So enthalpy has to do with energy changes in a reaction. So basically, if you have, so with thermochemistry, and some of you guys might not have covered this yet, kind of a later in the year thing, with a reaction, right? So let's say we have some reaction happening in this water bottle, right? We might have a reaction happening here, and then we have the surroundings of the reaction, right? So we have what's called the system and the surrounding. And basically the system and the surrounding makes up the entire universe, right? So if we have this reaction, and let's say it is releasing energy, right? The surroundings is gaining energy, we will have a negative delta H, or a negative enthalpy, because of the fact that the system is losing energy to the surroundings. Conversely, if we have an endothermic reaction, meaning the reaction is taking heat, we'll have a positive delta H, or enthalpy, due to the fact that we are gaining energy from the surroundings. Entropy, on the other hand, has to do with uncertainty, and has to do with chaos of molecules. So basically, how I'm trying to think. There's like a specific word, and I'm blanking right now. It's a measure of kind of disorder, right? So if we think of a solid, right, and we think of the molecular structure of a solid, it's very ordered, right? It's very grid-like. Whereas if we think of a gas, it's going all over the place. The entropy is higher. It's more disordered. And so with that, enthalpy and entropy can be used to determine things like how far a reaction goes forward, or how spontaneous a reaction is. And that's a word you'll really be using a lot when you learn these types of things. All right. I'm going to go through this, see if there's any ones that are upvoted more than others. Here we go. All right, would you be able to go over some stoichiometry problems, conversions of grams to mole and moles to gram? Yeah, of course. So let's pull this up. So I just want to make sure, do you want to go over like stoichiometry as in like limiting reactant problems, or just converting from grams to moles and moles to grams using the molar mass? I'm just asking for a quick clarification. Limiting reactant. Okay, let me pull up a quick. I'm just looking up a limiting reactant problem here. There it is. That's a good one. Okay, so we have that. Just give me one quick second to pull this in. There we go. All right, so here is an example of a limiting reactant problem, right? So we have zinc. Whoop, that's the eraser. We have zinc with reacting with 2 moles of hydrochloric acid to form zinc 2 chloride, yes, and hydrogen gas, right? It's just a metal reacting with an acid to form an ionic salt and hydrogen gas. That's a pretty typical reaction. So we want to see how much zinc chloride, and we'll then convert our answer to grams once we get moles, can be produced from the reaction of 2 moles of zinc and 3 moles of hydrochloric acid. And then we want to find out what is the limiting reactant. So really the way I like to think about the limiting reactant is what do we run out of first, right? We're basically, you can think we're using 2 hydrochloric acids for every 1 zinc. And so which one do we run out of first? We're using different amounts of the other in terms of moles. So the way I like to do this is take one of the moles, so for example, 2 moles of zinc, and convert that to moles of the other reactant to see if we have enough. So when we're doing, and this is another example of dimensional analysis, we want moles of zinc on the bottom. So we have 1 mole of zinc, right there. So we can just write mole of zinc, and then we have 2 moles of hydrochloric acid, right? And that's because of these what are called the stoichiometric coefficients on the reaction. So then we multiply, we cancel out our moles of zinc, and we see that we need 4 moles of hydrochloric acid to fully react with this 2 moles of zinc. So just draw this chart. Do we have 4 moles of hydrochloric acid? Just yes or no? No, we don't, right? We have 3. So therefore, we don't have enough hydrochloric acid to fully react with these 2 moles. So we know that the limiting reactant is hydrochloric acid, right? And our justification for that claim would be we need 4 moles of hydrochloric acid to fully react with this 2 moles of zinc. However, we only have 3. And so that's why we'll run out of hydrochloric acid first. So then from doing that, it's a fairly simple stoichiometry problem, right? We have 3 moles of HCl, right? And we want to use HCl because that's the thing we'll run out of first. And once we run out of one reactant, we obviously can't just produce more reactants. So we multiply this by, and again, we want to find out how much zinc chloride. So we have 1 mole of zinc chloride for every 2 moles of hydrochloric acid. And that's, again, using the stoichiometric coefficients in the reaction. So we get 3/2 moles of zinc chloride. So that's, geez, my dogs are going crazy today. So that's an example of how you would do a limiting reactant problem. And then from here, and I believe there's another question, so I'll kind of close this one and open another. We can then take this 3/2 mole of zinc chloride, right? And we can then convert that to grams. So let me close this question and I can open up that other one. Where are we? Compound. Good try, Jeffrey. Where is it? There we go. So how do you find, from Anaya, how do you find molar mass? Right. So we have zinc chloride. So let me pull up a periodic table, and I recommend you do the same because I don't know if I can share multiple tabs at once, but I will open this up and just reopen it. So we have P table. This is a website that I really recommend for chem students because it's just so helpful in terms of just a dynamic periodic table that you can look at. So what we want to do when we're trying to find the molar mass of zinc chloride is we want to find the molar masses of its constituents, those being zinc and chlorine, right? So we want to find zinc on the periodic table. It'll be right here at element 3. And its molar mass is 65.38. So I'm going to write that in the chat. So 65.38, and that's in grams per mole. We know that chlorine also has a molar mass of 35.45 grams per mole. Right? We can see that by looking at element number 17. So now that we've gotten that data from the periodic table, we can then go back to our problem, and we know that the molar mass of zinc chloride will be 65.38 plus 2 times the molar mass of chlorine, which is 35.45. Right, and we do that 2 because of the fact that we have 2 chlorines. And this will get us a molar mass of, let me plug that into a calculator, 65.38 plus 2 times 35.45 gives us 136.28. So now that is our conversion factor when converting, right? We want per mole of zinc chloride, we have 136.28 grams. These cancel out, and we have 3 halves times that number gives us 204.42 grams of zinc 2 chloride. So that's really the full process of stoichiometry. And the major thing with stoichiometry is this right here, taking the reaction and forming a conversion factor from the stoichiometric coefficients. So that's really the most important part of stoichiometry. Let me clear this. And we can move on to the next question. Okay, let me see. Does that make sense? If it didn't, then I can, run through it again quickly, or, just drop in the chat if something doesn't make sense. If it makes sense, perfect, awesome. All right. So from Jeffrey, who is Joe? So I'm going to take this question and I'm going to kind of put it back on all of you guys, right? Just ask yourself, who is Joe, right? Just ask yourself, and I'm going to, let that stew for a minute, right? All right. Okay, this is a great question. All right. How to name compounds, ionic and covalent. This is a really great question because naming compounds, you might have seen, I kind of just right on the fly, zinc chloride, right? That's really a skill. Skylight. Wow, I just lost where I was. When naming compounds, it's really a systematic way of looking at it. So there are 2 major groups, right? There are other little things like acids and stuff like that, but those are littler things that if you know the basic principles, you can get the covalent and the ionic, or you can get like acids and other things like that. So with covalent, we have the major thing with covalent is typically 2 non-metals, right? So 2 non-metals. If you guys can't really see this, I'll kind of zoom in here. So 2 non-metals. So for example, right, so let's do an example here. Let's look at the periodic table. NO2, right? Nitrogen and 2 oxygens. So what we do is we write out the name of the first element, right? Nitrogen. And then we have some prefix and then oxide, right? You always kind of give the anion version of the name of the second element. So for example, oxide, fluoride, chloride, sulfide, bromide, etc., etc. So the real goal of this now is just what is that prefix, right? Well, we know that the prefixes are just going to be based off of our numbers. Nitrate is a different thing. I think, actually, I might have just given us nitrate and without knowing. No, they're 2 different things, I believe. Because nitrate will have a negative charge, whereas NO2 with no charge is a different molecule. And I can give you another example because that was a poor choice of molecule. But yes, when you see NO2 minus, that is the nitrite ion. That's good. But when we see NO2, this has a name, right? And so we know that we have different prefixes for different numbers of molecules. So for example, 1 would be mono. Then we have di, tri, tetra, penta, and then it goes hexa, septa, octa, nona, deca. You really won't get past like penta or hexa, but yeah, hypothetically, yeah. So this would be named nitrogen dioxide, right? And you don't need the mono in front of the first element. However, if this was NO, it would be nitrogen monoxide, right? So for example, let's look at, let me make sure that's a real compound first. Perfect, yep. So let's look at this one. Try to drop the name of this molecule in the chat. Just take a minute and tell me what SCl2 is. My friend Jeffrey popping in saying, who's Joe, and then leaving. Sulfur dichloride, exactly, right? Because of the fact that we have one sulfur, and we don't need the mono, and then we have dichloride, not dichloride, dichloride. So that's really the major thing with covalent compounds. It gets a little tricky when you have like acids and stuff like that, but those are really secondary things. That this is the major part that you need to know. With ionic compounds, there are two major kind of species, I guess. So there's the metal, not metal, non-metal. That's the typical, you're always going to see that. That's going to mean ionic. However, when this metal is a transition metal, things might get a little funky. But let's just start out slow, right? So let's look at NaCl, for example, right? We have sodium, a metal, mixing with chlorine, a non-metal, right? So what we do is we just take it and we say sodium, right? And then we say chlorine, but then we have to add the anion suffix of "-ide", right? And "-ide" would mean a negative charge. So this is sodium chloride. Similarly, if we have Ca, let's say CaO2, or just, yeah, Ca, let's say ClCl2, right? This would still be named just calcium chloride. This wouldn't be calcium dichloride because we don't need those prefixes in an ionic compound, because we can tell from the charges on the molecules how there will be, right? Calcium has a 2+ charge, chloride has a -1 charge, and so we know how many there are. However, when it comes to transition metals, that's when things get a little funky, because of the fact that transition metals can take on more than one charge, right? So take, for example, iron, right? Iron comes in two forms. It comes in 2+ and 3+, and I'm sure there are others, but 2+ and 3+ are the most common. So if we want to find the ionic compound between iron and, let's say, oxygen, right? We could have two variations, right? We could have FeO, right? Or we could have Fe2O3, right? Oxygen's always a -2 charge. So this, we have iron with a 2+ charge and iron with a 3+ charge. So how do we differentiate between these two by the name? That's really the question I want to ask. And what we do is we add a Roman numeral to denote the charge. So here it would be iron 2 oxide, right? 2+ charge. And here it would be iron 3 oxide, right? So when you're looking at, when you're like on a test, if you were given this and told to name this, you want to first know, okay, iron is a transition metal, right? And you can see it's directly smack dab in the middle of them. We know then that this could vary, and we need these Roman numerals. So yeah, that's really how you name those compounds. All right. Let's see. Trying to find one that's been uploaded. There we go. What are the solubility rules that I have to know for the exam? Okay. I didn't memorize them. I just memorized commonly soluble things. Let me look it up, because I didn't memorize them, and I sure as heck don't memorize and remember them now. There's a list of common ones. So for example, you need to know that group 1 metal cations will always be soluble, right? You know, sodium chloride, calcium, calcium chloride. I always go to chlorine because it's easy. Rubidium sulfide, I don't know. Stuff like that, right? Those will always be soluble. Similarly, nitrates and acetates are usually are usually soluble. And then similarly, sulfates, ammonium groups, and group 17 or 7N halogens are typically going to be soluble. There are a few exceptions, such as lead, mercury, and silver, but really it's just a matter of memorization of those rules. And I'll drop a pretty good chart in there that I at least like to use. There we go. I'll just copy the image addresses from Quizlet. There we go. And if you click on that, it'll bring you to a little table. You don't have to memorize all of those, but memorizing things like the cations, nitrate, sulfates would be nice to know, carbonates, and hydroxides. Hydroxides are really important to know. So yeah. Okay, geez, we got a lot of questions. All right, let me see if any have been upvoted. Here we go. Can you explain chemical analysis? Can you kind of clarify as what you mean by chemical analysis in terms of like, do you mean stoichiometry? Do you mean, like, what do you mean by chemical analysis? Because that can mean a variety of things. Oh, okay. That's called combustion analysis, right? So it's basically thinking if we have some hydrocarbon, which is something with only carbon and hydrogen, and we blow it up, what happens, right? And so let me look up a problem. I'm trying to find just like an empty one. This was always the one that I'm really bad at. I was never great at combustion analysis, and I'm not. So I might honestly stumble a little bit on this because I don't remember much. But I'll do my best. So here's the problem. I get in here. All right. Okay. So we have a hydrocarbon fuel is fully combusted with 18.214 grams of oxygen, right? So that's how much oxygen we have to yield 23.118 grams of carbon dioxide and 4.79 grams of water. So we have something like this, right? We don't know the actual formula. It's just some hydrocarbon, right? Hydrocarbon fuel is fully, or some hydrocarbon is just HC plus O2, some amount of O2, right? And we know that a combustion will always yield carbon dioxide and water, right? So what really we want to find out is just what is this empirical formula, right? What is the most simplified version of that formula? So we know that we have 18.214 grams of oxygen, which we can then convert to moles using the molar mass of oxygen, right? So this is actually O2. And so the molar mass of O2 is 16, right? So we have 16 grams per 1 mole. And we're given 18 point whatever, 214 over 16 gives us 1.14 moles of O2, right? So we have some moles of O2 reacting to yield 23.118 grams of carbon dioxide and 4.72 grams of water, right? So if we want, the only place you can really go, can't we do 2 moles per 32 grams? Oh yeah, I'm dumb. I said 16 instead of 32, and we're dealing with O2. Good catch. Yeah, the diatomics are always kind of finicky with stuff like that. But it would be 1 mole, right? It'd still be 1 mole because it's 1 mole of O2, not 1 mole of oxygen. All right, so we're going to do 18.214 over 32, which gives us let's call it 0.57, right? Oxygen. Right, and we know that this reaction, that this is fully combusted, which means our hydrocarbon has to be our limiting reactant, right? So now we know that this hydrocarbon is combusted to form CO2, which is, so we have 23 0.118 grams, right? So let me plug this into a calculator. Oh my goodness, my dogs today. They're not having it. So what we want to find out basically is when we're dealing with an empirical formula, we want to find how many moles of carbon and hydrogen are in this, right? Because then if we can find that, we divide by the lowest amount of moles, and then from there we're given the empirical formula. And we know that because this completely combusts, all of this carbon is going to end up right there, and all this hydrogen is going to end up right there. So we want to find out basically how many moles of carbon are in this much carbon dioxide. So first things first, let's get that into moles. So CO2 molar mass is equal to 44, let's call it, right? So 44 grams per mole of CO2 gives us 23.118. I'm like scrambling on my keyboard here to try to get up open calculators and stuff. 0.118 over 44 gives us an answer of 0.5, let's call it 0.53, right? 53 moles of this is carbon dioxide, right? This isn't carbon. However, we know that for every mole of carbon dioxide, there's going to be 1 mole of carbon. We can just know that by looking at the formula. So that implies 0.53 moles of carbon, right? So now we do the same thing with our water, right? So we would do 4.129 9 grams of water times the molar mass of water, which is 18, over 1 mole. We want to include our units, cancel out the grams, and we get this is equal to 4.129 divided by 18 gives us 0.223. Let's see. Why is 0.53 moles of carbon? So let's think about carbon dioxide, right? So we have 1 carbon bonded to 2 oxygens, right? And I'm not going to bother with the Lewis dot and all that stuff, but we just have carbon bonded to oxygens. That means that for every mole of this, we will have 1 mole of carbon and 2 moles of oxygen, because we've doubled the amount of oxygen than we do carbon. So if we have 0.53 moles of CO2, we're going to have 0.53 moles of carbon because of the fact that we have 1 mole of carbon for every 1 mole of, yeah. So for example, if we wanted the amount of oxygen, we would then multiply 0.53 by 2, right? So that's a really important way to be able to look at, percent by mole. So now we have, and we'll see that right now. So 0.23 moles of water. However, look at this. We have 2 moles of H2, right? So we have, or 2 moles of hydrogen, right? So we have 2 moles of H for every 1 mole of this. So we multiply this by 2 to get 0.46 moles of hydrogen. All right, so now we know how many moles we have in each one. We have 0.46 moles of hydrogen, 0.3 moles of carbon. So now what we want to do is we have now a normal limiting reactants problem, right? We have the amount of moles of each. We will divide by the lowest mole. So we'll have 1H, then 0.53 divided by 0.46 to give us 1.1, let's call it 1.15. So now we want to multiply this by something so that these both become whole numbers. So for example, not 2. I'm trying to find the correct number since we got kind of a weird answer. I believe it's, yeah. So if we multiply these both by 6, we'll get 6 hydrogen and 9 carbons. So we can say that, no, wait. I screwed it up. 1.15. Like I said, I'm really not great at these problems. So basically what we want to do is find some whole number or some number to multiply this both by to get a whole number for carbon, right? So if we multiply it as, sorry. So I'm just plugging things into a calculator right now, trying to see what we can do. This one's a really weird one. So we have carbon is equal to 53, 47. So we get an answer of, yeah, that can't be right. Basically, what you want to do with these types of problems is get down to this level right here. We might have just made some rounding errors or something that kind of screwed up our result down here. But you want to find the number of moles of each present and then find the empirical formula through that. So yeah. All right, let's move on to the next question. There you go. Any tips for stoichiometry? I always get confused by the multiple mole ratios and seem to get these problems wrong a lot. Yeah, so stoichiometry is a really important skill in chemistry. So really the first thing that comes from stoichiometry is just balancing equations, right? So let's look at a simple one, right? We have H2 reacting with O2 to form water, right? And all we can do is add coefficients here, here, and here. So we can say we want to balance the oxygen, so we can put a 2 here. And now we want to balance the hydrogens, so we put a 2 here, right? That's our balanced equation. So now, with the mole ratios, the mole ratio is a conversion factor, right? So let's say we have 3 moles of oxygen, right? And let's just assume we have excess hydrogen. Yeah, definitely, Julia. So we want to multiply this, and let's say we want to find how many moles of H2O come out. Well, we know that we're going to have 2 up here because of our coefficient up here, and we'll have 1 mole of O2. And the way we got these numbers was by looking at the equation. And if there's nothing there, obviously, it's a 1. So it's a matter of dimensional analysis, not a matter of memorizing all these ratios. So then from there, we know that 6 moles of H2O will come out. Right, and then from there, we can do whatever else we have to do with the stoichiometry and with the, problem, whatever. But that's really the major thing with stoichiometry is applying those mole ratios. And it's really something you will get very good at, very bored with very quickly. All right. Here we go. My friend was upvoted. Here we go. How do I find grams of a solute given the grams of solvent and the percent M over M? What did Vanessa, what do you mean by percent M over M? Is that like molarity, molality? Like, what is that? Mass over mass. Oh, you're saying, so you're saying, for example, if we say we have like 100 grams of water, right? Tell me if I'm right, because I'm still kind of figuring out what you mean by your question. 100 grams of water, and then we want to find the grams of, let's say, sodium, sodium plus dissolved in here, right? And we're given the percentage mass over mass. So do you mean like the percentage to mean like that there's some gram of sodium per 100 grams of H2O, and that's a percent? And that's some percentage? Is that what you mean? Like grams of solute over grams of solution. Okay, so like this. So you mean like this, right? Trying to find out the grams of sodium. Yes, okay. So if we're not given some sort of so wait, they'll give you some percentage. So they'll say this is equal to, let's say, like 30%, you're saying? I'm a little confused as to what you're asking. Like, if you can give me like an example problem, that might be helpful. All right, I'm gonna wait for you to respond, and then we can get back to it, but I'm gonna move on for now. All right. So let's look at some of these other questions. All right, we'll wait for Vanessa to get back to us. All right, so what is Le Chatelier's principle? Okay, so Le Chatelier's principle really has to do with equilibrium, right? It has to do with how far does a reaction go forward. So I'm going to look up a good example of Le Chatelier's principle because I am too lazy to come up with one myself off the top of my head. There we go. So here's a reaction that does not go all the way forward, right? It would be H2 plus I2, right? We have a double arrow, yields 2 hydroiodic acid. This is not something, there it is. Okay, we'll get back to Skylar's question in a minute then. All right, I've really created a mess here, haven't I? All right, so let me paste this into Crowdcast. All right, so how many grams of sodium, oh, okay, I see what you mean. So how many grams of calcium nitrate need to be added to 400 grams of water to make a solution that's 12.5% by mass calcium nitrate? Okay, so we know that that the percent by mass is just some amount of grams of calcium nitrate, right? This is what it'll be, NO3 2, yes, per 400 grams of water. And we know that this is 12.5%, right? That's basically what the problem told us. So now it's just a matter of algebra, right? We can say that this is equal to 0.125, and then we multiply by 400 on both sides. So 400 times 0.125 is equal to 50. Right? We get this is equal to 50 grams. So it's just a matter of setting up the equation and then and multiplying out and doing the algebra in order to get your answer. Right. So let's get back to Skylar's question about Le Chatelier's principle. Right. So if we have this reaction right here, right, where we have hydrogen and iodine forming hydroiodic acid, and this has some Kc value, right, less than 1, right? Let's just assume that this does not go all the way forward, right? And for those of you who aren't understanding what I'm saying, this is something that you'll look at a lot later in the year. Definitely, this is definitely a kind of later topic. So yeah. So when we have an equation like this, where it doesn't go all the way forward, we want to look at Q, right? When we have Q, this is equal to HI squared over H2 times I2, right? And this will get this. You might say, okay, well, this looks a lot like K, right? And in many ways it is. However, these things that we put in right here are the current concentrations, not the equilibrium concentrations. So that's what separates Q from K, right? So what Le Chatelier's principle says is basically we can shift this reaction more to the right or to the left by changing these numbers, right? So let's say, for example, we dump a bunch of hydroiodic acid into here, right? Therefore, we're going to make this number here a lot bigger, and therefore Q is going to become greater than K. And when Q is greater than K, the reaction shifts to the left. The same goes if we dumped in a bunch of hydrogen or iodine, right? So for example, if we dumped now a bunch of, let me think, sodium iodide or something, right? Or something like that, right? Into here, we would now have this number getting bigger. We would see that we would see this number getting smaller, right? And so it would become Q less than K, and this reaction would shift to the right. So it's really a way to manipulate equilibrium and shift reactions to the right. It can also be used to determine whether or not a reaction is endothermic or exothermic. So let's just assume that this reaction has a delta H that is negative, right? It is exothermic. That means that heat, wow, my voice, hello. That my heat is essentially a product of this reaction. We're losing heat to the surroundings. So what we see is now if we increase the temperature, right? Let's say we increase the temperature. We're not necessarily affecting Q, but we are taking this heat and we are adding basically we're kind of increasing, think of it like increasing the concentration of heat, and then that will actually drive this reaction that way, right? Similarly, it's the opposite for an endothermic reaction. So does that make sense, Skylar? Just how I described the Chatelier's principle in that way? Just drop in the chat, Awesome. All right. We've got a bunch more questions here. Feel free to ask any more questions, even if we are coming up on 45 minutes to an hour. If you have any questions about stoichiometry, any more questions about naming or anything really, just feel free to drop that in the chat. All right, let's see. I'm kind of now, there's no outputs. I'm kind of just picking as I like. How can I find the pH of a buffer? I really like this question. So a buffer is a solution, right, of an acid and its conjugate base. So for example, if we see, let's take, for example, I'm trying to think of a weak acid now, acetic acid, right? If we have CH3COOH, right, this is an acid, right? It's maybe not a strong acid. It actually has a Ka equal to 1.8 times 10 to the negative fifth. Don't ask why I have that memorized. I do. Right, so it's a weak acid, which means that we know that its conjugate base, which is acetate, right, is going to be a significant base. It might not be a strong base, but it is a base with non-negligible basicity, right? It will affect the pH. So when we have a solution of both of these things, it creates what's called a buffer, right? If we add H plus into here, we're going to see that that's just going to form, right? We're going to see that this is going to react with it. And if we add a bunch of, let's say, hydroxide, we see that this acid is going to react with it. So it is a solution that is resistant to changes in pH. So the way we calculate this actual buffer is that we have the pH is equal to the pKa of the acid plus the log of, there's a specific order, and I can never remember the order. Literally, I looked at that equation probably 12 times on the exam, right? Of the conjugate base, the concentration of the conjugate base, over the concentration of the acid, right? So, for example, for this example, the pKa is around 4.74. Again, don't ask why I have that memorized. Plus the log of, let's say we have 0.5 molar sodium acetate in there, right? So acetate, and then 2 molar acetic acid, right? So now from here, all you have to do is 4.74 plus the log of this ratio. So it's the log of, what's 0.5 over 2? I should be able to do that in my head, but I'm too lazy. I believe it's 4, but it's 1/4, right? Times the log of 1/4. So that means that the pKa, or the pH, is 4.74 plus the log of 0.25, which gives us an answer of 4.14, right? Is equal to the pH of that solution. So that's really how you find the pH of a buffer, right? And this will be really necessary when looking at things like acid-base titration, which is something that you'll look at very much later in the year, because of the fact that when you have both an acid and its conjugate base present, you will always have a buffer, right? Unless you're dealing with a strong acid or a strong base. But that's for later. This equation has a special name. It's actually called the Henderson-Hasselbalch equation, right? So that's an equation, you're given it on the exam, and it's something that's really important to know by May how to apply it to acids and bases. Right, so does that make sense? You know how that, perfect, all right. Yeah, and again, if anyone has any more questions, feel free to drop those in the chat. All right, let's keep chugging through. All right. Where is it? How can I differentiate between the 3 types of intermolecular forces? I really like this question because intermolecular forces are super fun. So there are 3 main types of intermolecular forces, right? There are dipole-dipoles interactions, right? So I'm going to write dip, right? There are, there are London dispersion forces, which on the right, LDFs. And then there are, actually, there's a couple. There's more than 3. There's London dispersion. There's dipole ion, right? Then there's, yeah, those are the 3 main types. Because then under London dispersion forces, you'll see things like dipole, induced dipole, and induced dipole, right? And under dipole, you'll see things like hydrogen bonding, right? So to differentiate between the more than 3, you want to look at basically the structure of what you're looking at. That's why typically most teachers before teaching this will make sure you understand things like Lewis dot structures. So, for example, let's take a look at, everyone's favorite H2O, right? If we have the right here, and then we have to draw our valence electrons or lone pairs. So we know, wow, my whole nose just decided to clog up. So we know from looking at the structure, this is a polar molecule, right? It is asymmetrical. So we know that this will definitely exhibit, it will exhibit some form of dipole, right? If we have, I'm going to redraw this in a nicer way. If we have, right, so if we have our oxygen over here, and our hydrogens here, let me just get this up here so I can get those lone pairs in there. We know that this will have a dipole in which the electrons are shifted this way, right? And let me just write, there's like a special thing to do, something like that. Right, and so we know that this will have a negative partial charge. I'm going to write sigma negative. And we know these hydrogens will have a partial positive charge, right? It's not a -1 or a +1 charge, but it is a polar charge. So when looking at this, now we know that when we see another water creep up, it's going to orientate itself like this, right? Because we have our partial negative and our partial positive, and we know opposites will attract. However, when we look, we have a hydrogen having a dipole with an oxygen. So this means that we see a special super strong type of dipole bonding known as hydrogen bonding, right? So what hydrogen bonding is basically when we see a dipole interaction between hydrogen and either, the 3 main ones are nitrogen, oxygen, and fluorine, NOF, right? So when we see that, we really want to know, okay, these are going to be strong dipole interactions. Unlike that, if we have something like, let's think about, making sure that I'm correct here so I don't give you, right. So let's look at ammonia, right? We have NH3. We have H, and then a lone pair right here. Right, we can see that this is asymmetrical once again. So we know that we're going to have a partial negative here and partial positives here, here, here. However, no, we're still going to see hydrogen bonding in ammonia. We have that nitrogen and that hydrogen. However, if we have a polar molecule that that doesn't have hydrogen or oxygen or anything like that, we won't see hydrogen bonding take place. So, for example, iodine chloride, right? ICl. This is a metal and a non-metal, or no, it's not. It's 2 non-metals. So we know that this is going to look like this, right? So then we're going to see that this is not symmetric, right? So we're going to see that iodine will have the partial positive, and this is by looking at electronegativities. And so we know that when another iodine chloride pops up, we're going to have something like this. We have a partial positive, a partial negative, and we have that dipole. But that's not a hydrogen bond. It's just a dipole interaction. So, normal dipole. With dipole ion, the really only real usage of a dipole ion force is when you see something dissolving in water. So, for example, if we have a sodium ion, we're going to see the negative pole of water pull up and surround it, right? And so this isn't an ion-ion, This is an ion dipole because we see partial charges pulling up, and right, we have our partial negatives, and that's why actually that's how dissolving works. We see those ion dipole forces kind of take over. With London dispersion forces, they're always there. London dispersion forces will always be present. So for example, if we just have like, I'm trying to find a good example here. Right, if we have, for example, I'm trying to find just an example, like, let's look at methane, right? CH4. This is nonpolar. Right? It's a perfectly symmetrical molecule. It's nice and pretty. However, it is still going to have extremely weak dipole-dipole, or induced dipole interactions due to just randomness of electron clouds, causing some very instantaneous dipoles to occur. So that's really, really how intermolecular forces work. And then based off of the strengths of these intermolecular forces, so for example, hydrogen bonding is really strong, London dispersion, not so much, we'll be able to see, what will happen, what causes those differences in the actual properties of the molecules. All right, and for those of you who are just now joining, feel free to drop another question if you'd like, or just feel free to watch. All right, so just what is the kinetic molecular theory? All right, so the kinetic molecular theory is basically a theory derived about gases, right? So if we have a container of a gas, right, let's just draw particles of gas. We don't care what it is really, but this is just gas, right? It fills its container, and it will, it'll act like a gas. So the four principles of kinetic molecular theory are that a gas consists, first of all, of random motion, right? These are just whizzing around, right? They're whizzing around. They're not moving with some sort of, they're not moving with some sort of like structure. They're just bouncing around. We also say that they're moving in straight lines, right? We're just saying that this molecule, for example, is just like that. This is moving like that. And for those of you who are taking physics, vectors might come to mind. So we see these aren't the straightest arrows, but these are all just whizzing around in random directions with random kinetic energies, or actually, right. And they do have kinetic energy, right? We also say that the collisions between molecules are what we call completely, my goodness, what we say are completely elastic, right? When we say completely elastic, we mean that when molecules collide, there's no exchange of energy. In reality, that's not true. There is a small exchange of energy. There has to be, based on the law of conservation of energy. However, we can see here by the kinetic theory of gases that they're always in motion, and that that is completely elastic, right? We also assume that there's no intermolecular forces going on here, right? We can assume that in a gas, the IMFs are relatively weak, because if you have a gas, right, we're moving all over the place. We're not going to really have time, I guess you could say, for forces. And then a fifth important fact of the kinetic molecular theory is that the average kinetic energy, right, so the kinetic energy average, is directly proportional, that's the sign for proportional, to the temperature in Kelvin. So for example, if we increase the temperature, what will happen to the average kinetic energy of those molecules? Just take a guess, right? Increase, decrease, stay the same. We increase temperature, what happens to basically the speed of those particles? Just drop in the chat. It increases, exactly, right? So when we add energy, it makes sense. We add energy, things are going to go, right? And I know my sound effects are just fantastic. It's a talent of mine. So yeah, so we also see that explains why pressure exists, right? When we look at pressure, it's really just molecules bouncing around off the side of the container. And so that's also why some of the laws that we look at, for example, like, I'm forgetting all the names. So for example, we look at, I'm making sure that I'm correct here with the actual, right? So for example, what's called Gay-Lussac's law, right? It basically states that if we increase the temperature, the pressure will increase, because the faster they're moving, the more pressure they will exert on the sides of the containers. We also see Avogadro's law come out of this. We see Boyle's law, right? The pressure and the volume. Think about it this way. If we decrease the volume of this container like that, and we have the same amount of particles, we're going to see a lot more collisions within the container, right? And so that's why the pressure increases when you decrease the volume. My God. Right? Let me make sure I'm correct on saying that, because I don't want to give you guys... Right, as pressure increases, volume decreases, and vice versa. Right. So then you can really use the kinetic molecular theory to think about not only those laws, but also the exceptions to the ideal gas law. Right. That's the reason why some things we have certain exceptions. Okay. How do I calculate the bond enthalpy of a reaction? All right. This was always, for a while, my least favorite thing to do. So I'm going to pull up actually an official AP problem, because there was one that was kind of neat that I would like to share with you guys, if I can find it at least. There we go. So let me get this reaction in here. So basically, this question is going to be a little bit of a spin on what you typically will see about kinetic energy, about bond enthalpy of reaction. So here we're given, and this is from the 2019 free response question. So you can go take a look. It's from number 2, I want to say, yes. And so now let me get the question in here, right? This was part G from the question. So this will give you guys a good taste of what it's like to actually do an AP question, and I'll walk you through it, don't worry. All right, so we want to, so part G is asking us to calculate the bond energy of the bromine-chlorine bond, right, in kilojoules per mole. Right, we're good, our units are all the same. For the reaction, they repeat the enthalpy for us, and the information in the following table. Okay, so let's take a look at just the formula right now. It's going to be kind of simple, but trust me, it's not that bad. So basically we say that the enthalpy of reaction, right, is equal to the sum of bonds broken minus, let me make sure, wait. I'm going to make sure, I always screw up the order on this. So I'm going to, yes, okay, I got it right. Look at me. So bonds broken minus the sum of bonds formed. Right, and that might look really scary because of all the Greek letters and all the, what's going on? But basically all it means is we take the amount of energy released from the bonds broken and subtract the energy like inputted, I guess that's a bad word, but put into the system to form those bonds. So for this, so we know that the bonds broken in this reaction is basically, and I like to kind of draw a picture, is we're going to have to break 2 BRCLs, right? And then we're going to have to form, right, a BR-BR plus a CL-CL, right? Think about it this way. You break those 2 bonds and then you form the new molecules. So now what they're asking us is to calculate this number right here. So we don't know this yet. However, we do know that we're going to get 1.6 kilojoules per mole, right? So we know that this is a positive number. Right. So we have 2 times, I'm just going to call it X for now, but we know that it's the bond energy of the bromine-chlorine bond minus, so bromine-bromine is 193 from the table, plus chlorine-chlorine, which is 243. So we get 2x minus, damn, my handwriting is really falling apart, 193 plus 243. Gives us 436. So 2x minus 436 is equal to 1.6. So then we want to just, and now here is just algebra, right? So we have 437 0.6 is equal to 2x. So 437.6 divided by 2 gives us 218.8 as our answer. Right, so that's really what they'll want you to do. They won't sometimes ask you to calculate it, and they very well could. It's a valid question. They might also want you to apply it. And let me just check our answer real quick to make sure I did that correctly. Right, 218.8. Then when we do the sig figs, right, it's equal to 219. Right. So does that answer your question, Skylar? All right. All right, we're going to probably go through 3 or 4 more of these. So how do I determine the Gibbs free energy of a reaction? So as much as I hate to say it, Gibbs free energy is not a measure of something like Harley, unfortunately, but we made that joke too many times in my chemistry class. So Gibbs free energy is a really kind of neat measure of thermodynamics, right? It measures basically the spontaneity of a reaction, which has to do with how far the reaction goes forwards, right? Does this reaction happen, or do I kind of have to like give it a nice little nudge, right? And so the technical formula for it is delta G standard is equal to delta H standard minus T delta S standard, right? Or most people say delta G naught is equal to delta H naught minus T delta S naught, right? We just say naught instead of standard. And so that's the formula, right? So if you're given the enthalpy of the reaction and the entropy of the reaction, you can find the Gibbs free energy of the reaction. And again, if it's negative, that implies spontaneity. If it's positive, that implies that it's non-spontaneous, right? We also can say that delta G naught is equal to negative RT ln K. That's another reaction due to the fact that we have a relationship between K and delta G, right? And this R here is 8.314 joule per gram. I forget what it is. Let me look at the units again. It's something like that. It is, the R energy constant is, oh my god, 8.314. It's 8.314. That's what's important. I can find the units later. It's 8.3. Okay, there it is. 8.314 joules per mole K. Right, that makes more sense. Right, which then you can convert that to kilojoules by doing dimensional analysis, which we talked about earlier. So that's really how you would find delta G. You might be expected also to do it by the same product minus reactants rule you can apply here and here. However, it's kind of less common. You'll probably be just using that formula. All right. So some of these questions have kind of basically been answered. So I'm going to delete a couple of them. All right. How do I calculate molar solubility from the solubility product constant? So the solubility product constant is the same as just any other K value, right? It's KSP, solubility product, right? So let me look up a problem here. Right, so we want to calculate the molar solubility here. Let me get the problem up here first, and we can start talking about it. So it's asking us to calculate the molar solubility of lead-2 chloride in pure water. And they said the Kp of lead-2 chloride is 1.17 times 10 to the minus 5. So we already know that lead-2 chloride is not very soluble, right? That is a non-spontaneous, that is a very that is a reaction that will reach equilibrium very, 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 very low concentration-wise. However, we know that lead-2 chloride, right, PbCl2, will dissolve. It will technically, to an extent, into lead-2 and Cl and 2 Cl minus, right? That's just how dissolving works, right? You break it up into its ions. So then we know that the KSP of this reaction is equal to, it's just going to be equal to the concentration of Pb2 plus 2 Cl minus, or plus Cl minus squared, right? And the reason we don't have this is because this is a solid technically, and we don't include solids in the equilibrium constant, right? So then what we want to do is set up what's called an ice box, right? Or a rice box for some, but ice box, rice box, whatever. So we say initial change equilibrium, right? So here we can ignore this whole area. We don't care. Our initial concentrations here are 0. We don't start out with any. And we're going to add x amount of here, x and 2x here. So x and 2x, right? And that's just because we know the stoichiometric coefficients. So then we can do, this is equal to x times x squared is 4x squared. So then we get 4x cubed is equal to whatever that KSP was, 1.17 times 10 to the minus 5. And then we would just have to do the actual algebra. And in this case, we're lucky, we just have to find x. However, if in here was like a 3x or something, or like if this was like x squared, then we'd have another story, right? So we're just x there. So that's what molar solubility is, right? How many moles can you dissolve in here? And that's really described by the concentration. All right, let's keep going here. How do I explain why the atomic radius of one element is more than the other, or why the ionization is less than the other? I'm going to assume you mean, when you say ionization, do you mean ionization energy? I'm pretty sure you do, but I just want to make sure of it so that I'm not, Yes, okay, perfect. So with atomic radius, I'm going to pull up my handy dandy periodic table here. See if my tabs are on that. So, right, here's our periodic table. We know, so let's start with ionization energy, right? Think about it this way. When we are going across a period, we're adding electrons, right? I'm going to open up this orbital tab. So for example, actually, no, there's a properties tab. So if we want to look at first ionization energy, right, we can see that the trend is that it increases going down a period, right? It goes increases, and then we see a little dip, maybe right here, right around here. That's because of the metalloids and how they act and stuff like that. However, so when we are looking at why does this increase as we go across, it's because, so the first ionization energy is the amount of energy required to knock off an electron, right? To knock off the first electron, to be precise, right? So as we start moving across here, if we look at something like cesium or francium, we see that these ions, or these electrons, are really not that stable due to what's called the shielding effect. So if we look at, I'm going to pull up a Bohr diagram of cesium, right? Cesium. So let me get out of here and open this up. There we go. Right. If we take a look at this image right here, right, and right. If we take a look at this image of cesium right here, and I'm going to try to zoom in. I think it doesn't really work. Right. We can see that there are a bunch of electrons. Oops, I got rid of it. I'm dumb. I'm really dumb. Okay. Here we go. So we can see that there are a lot of electrons in those inner shells, right? And these colors just indicate the orbitals that they're in. But we can see that and I want you to answer this, what do electrons do to themselves? Like, what do you get when you have an electron next to an electron? You get an electron, what? Repulsion, attraction, just answer in the chat. Do electrons repel? Do they, what do they do? They don't give electrons, but what do electrons themselves do together, right? If you have an electron next to an electron, they have like charges, meaning that like charges will repel, right? So this is what's called the shielding effect, right? It is shielding, these electrons all down here are shielding the effect of this nucleus making this electron a lot easier to just rip off. Whereas if we're looking at something like hydrogen or helium, so not only does helium have that full octet, meaning it doesn't want to give up electrons, it is a stable electron configuration, it also doesn't have very much shielding, right? So moving down a group, that's why it decreases. Moving through a group, you're getting closer and closer to a full shell, meaning that an element is less and less likely to give up that electron. Similarly, when we're talking about radius, right, going down a group with a radius, you're just adding energy levels, right? Whereas when we're going across, we're seeing that the effective nuclear charge is increasing, meaning that the essentially is getting tighter and tighter and tighter, right? We're getting more protons, we're getting more force, right? And so we are seeing the atom get smaller and tighter, meaning that the actual smallest element is in fact helium and not hydrogen. And as we move across, we get smaller and smaller and smaller, right? So that's really how that works. All right, so I know we still have questions. I think we're going to call it here. It's been a little over an hour, and there doesn't seem to be any other questions that really we can answer right now. So I'm just going to kind of hang out for another minute, see is everything, is everyone okay? Just if you have any more questions in the next 10, 20 seconds, feel free to ask them. But if there are no more questions, I think that we're good then to sign off for the night. So yeah, that was the stream, AMA. If you have any more questions, feel free to ask them in our other streams. We have, let me check, we definitely have streams coming up for Chem. I think I have a stream tomorrow on AP Chemistry. Yes, on intermolecular forces. So whoever asked, or intramolecular forces, right? So for the person who asked about those intermolecular forces, that stream would be good for you. So yeah, I will probably be streaming again in the next couple of weeks, and yep, I will see you guys in a bit. All right.